Hello everyone, welcome back on the course on higher surveying, and we are in the last lecture of module 3. In this module, we have already learned 3 lectures. In the first lecture, we have find out what are the reference system for the astronomy, and we say that there are 4 systems. And then we find out that declination and right ascension are the independent coordinates with respect to the Earth. We are measuring these coordinates, declination and right ascension, using some fixed point and using some fixed plane, that is celestial equator and vernal equinox. For that reason, they are not dependent on the rotation motion of the Earth, and hence they are basically coordinates which remain same for any user on the planet Earth. With this, we have talked about what are the possible applications where we can connect the 3 reference systems, and then in the last lecture we talked about time. In case of time, we learned that there are 2 possibilities of measuring the time. First possibility is to measure the time with respect to sun, that is what we call solar day, and there is another possibility where we learned that how to measure the time with respect to far distant stars. And we make the differentiation there that with respect to sun we call a solar day or solar time, but with respect to far star the rotation of the Earth is measured by the sidereal time. Okay, so that was the idea. We said that suppose you are sitting on a far distant star, in that case you will feel that Earth is rotating with the sidereal time, or Earth is completing 360-degree in a sidereal day. But if you are sitting on the surface of Earth, then you will feel that you are completing one day in one solar day or 24 hours. So that is the difference. So whenever we are there on the surface of Earth, we will use solar day, but if you are far away, for example satellite station or in the satellite or in some other star, we will use sidereal days. The meaning here is, if we are trying to study the motion of the stars which are far away, I should use sidereal days, and if I am trying to measure the motion of the sun or some other purpose which is mainly governed by the sun, for example our biological life or our civil time, then we should use the solar time or solar day. That was the idea. Now in this lecture we are going to do some applications of time and reference system for astronomy. So let us delve into this lecture, and that is the last lecture on this module, application of concepts of astronomy and time. Okay. Now again these are the books we have already recommended. Before starting this lecture, let us raise some queries. And the purpose of these queries is, we should first understand what are the basic problems that we are going to address by the knowledge that we are going to gain in this lecture. So once you have few queries beforehand, then you will try to respond to these queries. In the process, you will develop a knowledge base in order to respond to other questions also, if you have in future. So that's the idea here. Fine, let us go ahead. So the first query is, when will a star or sun will rise or sun will set? That's my first question. Remember, we have already realized that what do you mean by sunset? When sun is on 0-degree altitude with respect to given celestial horizon, we call it sunset or sunrise. So sun if ascending above the horizon, we will call it sunrise, and if it is descending down below the horizon, we call it sunset. But most important is, at what time? Why few stars always appear in night? They never set. So if you go to an open ground and try to see the stars in night time, you will find out at your place, irrespective of your location. That means even if you go anywhere in the ground, you will find out there are few stars, they will always remain in the sky, and every day you can observe them if you can identify those stars. Okay. Similarly, are there any stars which never come at your place, or are there any star like sun which rises and set like a sun? Okay. Now using astronomic observation, for example star or sun, can we find out the astronomic north? Okay. Also, can I find out the error of my watch? Why this is an important question? Because as we said, the time and celestial reference systems or the reference system for astronomy are connected to each other. Basically, when we said that we have defined some reference system for astronomy, we ultimately came to the point that I want to determine the rotation of the Earth. And by determining the rotation of Earth is determining the time. So, can we find out the correct time of my watch using some star observation? Okay. Then last question is, how can I identify the north direction without any astronomic observation using sophisticated instrument like total station, theodolite or any other instrument? What is some kind of common knowledge we should have? Okay, so let us look into these questions today. So in case of rising and setting stars, that means there are few stars which are rising, there are few stars which are setting, there are few stars which never set, and there are few stars which never rises above horizon. So I can visualize three possibilities here. What are these three possibilities? First is a star that never set below horizon, and we call it non-setting stars, and we also call them circumpolar stars. There are some stars which never come above horizon, and we call them the non-rising stars. And third category, which are rising and setting, that means they are like sun. They will rise above the horizon, they will pass through, they will culminate, they will make a transit on the celestial meridian of an observer, and then again they go to the west and they will set. Okay, in case of sun, we call morning and evening. That means in morning sun rises and evening sunset. What about the other stars? Well, morning and evening terms are not used. Rather, we say that star rises in east, make a transit on the celestial meridian, and then it sets in the west. Fine. In the second lecture of this module, we also calculated whether sun is exactly coming in the west or exactly rising in the east or exactly setting in the west by calculating the azimuth value. So you already learned some numerical process. Now, what do you mean by rising and setting? Okay, so let us come back to our original setup of celestial horizon and celestial equator, and this is a celestial sphere which is shown here. So we have zenith and nadir in place. Again, the north celestial pole, NCP, and SCP, south celestial pole, both are in place here. Okay, so let us go ahead. Let us say there are 4 stars as shown in the figure, and since we know that all the stars will appear apparently moving around the north celestial pole because of the rotation of the Earth. So these are the paths of the stars. Let us take the first star, which is star 1, and let us see its motion. So it is moving in a clockwise direction from east to west like this. Well, it is shown in the animation. So you can see that this star will always remain above the celestial horizon of an observer. Okay, let us take the next star, star 2. Here, if you see the star movement, now you can see the daily orbit of the star, where if I mark, and there are 2 points, these are the points where a star is touching the celestial horizon of observer. So let us see what is the motion here. So now a star is moving, now it is below the horizon, and now it is coming up, and now it is moving above the horizon, going down, coming up, and so on. So these are the movements of the star. The idea here is, this is the star which is going below the horizon and above the horizon. So this star will go as a sun, and it will set down, and again it will rise in the next day night. So it will appear as it is setting below the horizon, and it is again rising next day evening. So such stars are called rising and setting stars. For the third star, like this star 3 here, and this star is again moving, and now you can see that it has a longer period below the horizon compared to star 2, and as a result we can see that it will appear for very short time above the horizon. So when a star is above the horizon, an observer can see that. Now what about the daytime? Daytime, all the stars are there in the place, but because sunlight is so intense that we cannot see the other stars. But yes, stars are there in the place. Best example is the solar eclipse. At the time of solar eclipse, the complete eclipse, we can see the stars around us in the sky. Well, If you look at the star 2 and star 3, they are coming above the horizon and they are rising and setting. But what about the star 4 like this, which is never coming above the horizon, and because it is moving like this as shown in the animation here. Now you can see that even it is rotating around the earth, it is not able to come above the horizon because of its own position in the celestial sphere. Okay. So, how can I distinguish between a star which is rising or which is non-setting star, and there is another star which is non-rising star? That means non-rising star will never come above horizon and non-setting star will never go below horizon. So, non-setting star, which is called circumpolar star, will always appear in the sky with respect to the horizon. Okay. So, if I draw this kind of plane parallel to the celestial equator passing through the celestial horizon, that means this plane is touching the celestial horizon at this point here and it is parallel to the equator, I can see that this is the zone of non-setting stars. Similarly, if I draw a plane over this point and parallel to the equator, I can see that there is a plane like this, and below this plane all the stars will never come above the horizon. So, the zone below this plane is called non-rising star zone. Okay. What about the zone between the two planes? And remember, these two planes are parallel to the celestial equator, but they are passing through this point and this point. Now, the zone between these two planes is called the zone of rising and setting stars. Why? Because between these two planes, stars will be rising above the horizon and they will be going below the horizon after making the transit over the celestial meridian. Now, we have learned many times what is declination and what is the longitude and latitude of the place. So, I am writing this relationship here, where I can see that latitude of the place, if it is more than 90 minus delta, that is co-declination, the star will be non-setting star or circumpolar star. Similarly, you can find the other relation for the remaining stars. So, now I can write this relationship, that means the declination of the star is more than co-latitude, then that star will never set, it will be always a non-setting star. Okay. So, now you can just open the star catalog and find out which star is having delta more than co-latitude of your place, and those stars will never set below your horizon, or rather they will be circumpolar stars, or they will always appear in the sky every day. So, that is the idea here. Similarly, you can develop other definitions for non-rising stars and rising and setting stars. So, let us go ahead. What about the sun? Sun is a star which appears above the horizon and below the horizon daily. So, it is a rising and setting star. Okay. I have drawn the ecliptic, which is the annual path of the sun. That means, what do you mean by annual path of the sun? Annual path of the sun is similar to noting down a position of a star every day at same time. For example, let us say at 11 a.m. morning, you go to a rooftop and measure the declination and right ascension. You cannot measure them directly, but let us say you are determining it every day 11 a.m. at your place. So, that declination and right ascension, if you plot every day, you will get ecliptic path. So, that is the idea of annual path. So, you are marking those 365 positions along the equator of the earth, and you are getting this kind of path, which is shown here in red color. Let us remove Zenith Nadir and let us say sun is here. So, what about the daily path of the sun? We have marked one position on a one day on this ecliptic. So, daily path is parallel to the celestial equator. So, like this. Now, sun will move in this way and it will first set here and it will rise here. So, this is a rising point, I can say is around east, and that is the west here. Fine, let us look the motion by animation. So, the sun is moving here, right, and it will go below the horizon. Now it is night time, it is again morning and sun has come up above the horizon and now it is there. So, we have learned that at this given position, what is the motion of the sun in a daily path. You can see that above the horizon, the difference between east and west is longer compared to the length of the sun path below the horizon. And as a result, we can say that days are longer when sun is in northern hemisphere. You can see with respect to celestial equator, this is northern hemisphere, and this portion is southern hemisphere. Right. So, this is northern hemisphere above this equator plane. Well, so now the sun is in the northern hemisphere and as a result, I have longer day for a position of observer which is in the northern hemisphere. Now, let us look in the other position. Let us say sun is in the equator, that means this position on the ecliptic path. This is the daily path of the sun. Now, you can see that it is coming above the horizon here and here. It is setting down, right. So, this is the motion of the sun. It has just come above the horizon and now it is the daytime at that observer's location and now it is set here in the evening and again it is the night time when it is travelling, it is transiting through north and it has done complete one cycle. Okay. So, I can see here the length of the day and length of the night, that is the length shown here by the dotted line and the length shown by a firm line. So, the length shown in the firm line is the daytime and length shown in the dotted line on a daily path of sun is the night time. So, they are almost equal. Let us take the position of the sun in southern hemisphere, let us say around in month of November, December. As a result, you can see that is a daily path and in the daily path you can see that for observing northern hemisphere, the length of the day is quite small. Although it is an animated figure, it is highly exaggerated figure, but still it is conveying that the path from this point here east, here and to west, right, that is much smaller than path below the horizon. Further, let me specify more. So, length of the day for an observer in the northern hemisphere is much smaller if sun is in the southern hemisphere. And that is the idea we have experienced it every year because of the winters and summers and so on. So, in the northern hemisphere when summer is there, days are longer. In the last figure, it was little complicated to understand. In the books, you will find this kind of figure. So, we are also showing in a rotated form now. Okay. So, this is the sun here. So, sun is now rising above the horizon and now it is travelling in the day. Okay. Now, it is going down. So, very soon it will go below the horizon and now it is sunset here, right. So, it was a east point here and it was a west point here, opposite point is west, sun will be below the horizon. So, now it is in the night time, evening to morning is coming and the next day morning sun will again come in the direction of east, but not exactly east, it could be slightly northward or southwards. So, in the season of summers it comes slightly north way, then it passes through the south and that is why from north to south it will take long time and again south to again north further if sun is here. So, this is the point where sun will rise and sun is moving above the celestial horizon. So, you are facing the daytime and this is the transit of the sun on the celestial meridian of an observer and sun is now going to set. It is the point where sun will set. Okay. So, sun is now below the horizon and you are feeling night time, right. So, it is a north transit here, lower transit what we call. So, after lower transit sun will again rise and it will come to the horizon of an observer. Okay, the third position again we are explaining here, because sun is in the southern hemisphere. So, this is the path of the sun. So, you can feel that sunrise to sunset time is very small, because the length of the path of sun is comparatively short above the celestial horizon of an observer. So, now this is the time you have in the night after the evening, where sun is moving through the lower transit, what we call midnight. And now sun has come to again at horizon. So, that was the idea about the rising and setting star. So, sun is very special for the earth, because it is governing the daily life, all the biological life, as well as most of our activities are governed by the sun. Now, let us look into the application of time and the reference systems of astronomy. The first idea here is, I want to find out what is the direction where my astronomic north is located at my place. What will I do? I will make some star observation or sun observation and try to find out the direction of north. So, let us make the clock tower as reference mark as shown here. Now, I will measure the angles of a star or a sun with respect to the reference mark. Let us see, there is a sun. So, I am measuring this angle, and this is the astronomic bearing of a sun at a given moment. So, if I can find out this value, I can also find out the azimuth of the clock tower. So, then what will I do? I am measuring the angle theta. I know the position of clock tower. With respect to that, I will measure the value of theta for the sun at a given moment, and then I will find out astronomic bearing of the sun for that moment, and then I can deduce that if I go back like this, that this is the astronomic north, and from that north I can say this is the azimuth of my tower. So, let us say this is sun direction here shown by this pen. Okay, this is my clock tower direction here. So, I am measuring this angle here at a given moment, and by using some calculation I am finding out what is the angle that sun is making right now from the north, like this. Okay, so this way if I go back in this direction, I can find out this is north direction, and now I can say what is the azimuth of this reference mark, that is clock tower. So, let us see what is the process here. Remember that in our fundamental concepts of astronomy, we have assumed that we have done some calculations on the center of the earth. That means the observer is located on the center of the earth. More specifically, his eyes are located on the center of earth. So, I am performing all the calculations on the center of earth, for example, declination, right ascension, or hour angle, and so on. There is some contradiction, because we are observing the sun on the surface of the earth. So, now we need to make some corrections so that we bring our coordinates, that is, we are measuring on the altitude of sun. So, I will bring the altitude of the sun with respect to the center of earth and not with respect to the surface of earth. Let us look what are the corrections needed here. So, first correction we make for refraction. What is that? Let us see, there is a point P on the surface of earth, and I am assuming that the earth is spherical here with radius r. So, this is observer's horizon at surface of earth, and this is observer's horizon shown here at the center of earth. So, let us see, there is a north on the observer's horizon, and so this is the zenith direction, or the line showing here is vertical line. Now, let us see, sun is there right now. So, what will happen here? This is the sun, and I am going to measure this angle, and let us call this angle as alpha dash, because this is the correct angle I want to measure. But because of the refraction in the atmosphere, the rays which are coming from the sun, they travel some curved path, and because of that I measure higher angle. Let us see, this is line of sight. Why? Because the line which are passing through my eyes, that is line of sight, will curve and will curve down and it will reach to the sun. So, this is the line of sight, right. So, as a result, at a point where I am observing the sun, my line of sight is tilted up, and so I measure this angle shown in the red color called alpha, not the alpha dash, and I need to put some corrections for that in order to find out the alpha dash, and that is the correct angle. So the correction is CR for refraction, and alpha is measured value here. This correction is given by this value in seconds. Remember, you should put your alpha value here. You measure 23° alpha, for example, put this value here and you multiply with 58, you will get corrections in seconds, and that will be the negative, because we know alpha dash is smaller. In the books you will see this kind of figure. Now let us look for the correction of parallax. The parallax is generally termed as the change in the angle because of the successive exposure. Let us see, this is the earth and you are at point A on surface of earth. So now it is your sensible horizon, where you feel as if there is a horizon like this at a given place. This is the sun and you measure this angle, which is called alpha here, like this. Fine. We have assumed that the observer should be located at the center of the earth. We have defined celestial horizon as well as celestial equator passing through the center of earth. So now we should measure the angle of sun with respect to the true horizon or the celestial horizon, which is containing the center of earth. So this is the correct angle. So I should measure alpha dash, not the alpha. I need to apply correction for the parallax, and this correction is given by Cp in seconds. Okay. So you put the value of alpha here that you measure, and then you find out this Cp. Again it will be positive correction as visible from the image, that angle alpha dash is more than alpha. So we will put a positive correction here. So let us take the third correction, that is correction for dip of horizon. We have assumed that the observer is at center of the earth, but we know that observer is on the surface of the earth. Moreover, it is not exactly at the spherical shape of the earth, it is above that, and what we call the elevation of the surface above the MSL. So it is like that. Let us say it is earth and it is origin, and let us say it is radius r, and let us say this is a terrain. This is the point A, which is above the mean sea level at an elevation of small h, and this is the sensible horizon, or what we call is observer's horizon or true horizon. This is the sun. So I am measuring this angle. We have termed the true horizon at point A. Remember, I should draw it parallel to the sensible horizon, but it should pass through the center of earth. But here we are still calling it true horizon because we have already made correction for the parallax. So now assume that I have already made a correction for parallax and I am getting alpha dash value, not the alpha. On top of that alpha dash, I need to understand that location of observer is situated on the height h above MSL. He has a different horizon, right? He will look towards point D as a visible horizon. That is called the visible horizon because it is our tendency to look around, and obviously from the point A we are finding a point which is lying at the horizon, but that is lower than the point A. If I extend the line of sight, you will find out there is a point on the visible horizon, and this is the point D. Now as a result I will measure this angle, right, and let us call this angle as alpha. This is the angle I measure and this is the angle I should measure. So this is the alpha dash here. Okay. So the correction here is beta angle, and this correction I am writing here like this. Beta is negative because alpha dash is smaller than alpha. So this correction is given by this. So this is the lower one, is the approximate value here. This is an approximate value and this is the exact value. Well, the height of the observer above MSL is much lower compared to the radius r. So radius is in order of 6400 kilometers, and MSL height could be in general around maximum 500, 600 or maybe 1000 meter. The MSL height of Nainital is 2000 meters, and if you compare 2000 meter with 6400 kilometers, it is negligible. But if you go to the Himalaya or higher altitudes, it will be higher. Okay. So now we have put 3 corrections. Let us look into the fourth correction, and that is correction for semi-diameter of sun. Let us say this is earth and that is the horizon at the center of earth. It is the direction of zenith. This is the true horizon because it is passing through the center of earth. Ideally I should measure the center of the sun, but I do not know where exactly center lies. So what will I do? Either I keep the crosshairs at the lower edge of the sun or at the upper edge of the sun. So I should measure this angle here, right? Okay, but I measure either this angle or I measure this angle. Okay, so whichever angle I measure, I need to put either positive correction or negative correction. Let us see, this is the diameter of the sun as gamma, and it has some value given by 31 minutes 32 seconds in July. It appears to be dilating in January as 32 minutes 36 seconds, but in general average value we take as 32 minutes and 2.36 seconds for our calculation purpose. Now, these are the 4 possible position of crosshairs to make sun observations. If I am making the sun observations in this situation, I need this correction and that will be positive here, right? And if I make this observation, then I should put this correction here positive, and if I make this observation, then I should put this correction as negative. Similarly, if I make this kind of observation, I should put this correction negative. You can see in the first position as well as in the fourth position, let us say B and A here, I will be putting corrections to the altitude value. For the C and D here, and I will put corrections to the azimuth value or the horizontal angle value, and I can draw this table for the corrections. So now you can read this table. So if I am measuring for this situation C and D, then I should make this correction for azimuth angle or horizontal angle, this or this, positive and negative. But if I am measuring the altitude angle in this position, then I should make corrections. This is negative and this is positive correction. Okay, now we have made correction for semi diameter. So we have made total 4 corrections to the measurement of the sun observations. So now we understood that if I measure the altitude of the sun, what kind of corrections I should make. Okay, so let us go ahead. Now try to learn what is the procedure to observe the sun in order to make the calculation of the azimuth of the reference mark or finding out the true astronomic north. So first of all, we have a theodolite or an angle measuring instrument and clock. It could be total station electronic theodolite or mechanical theodolite. I am looking at any object with these crosshairs. So I am putting my object somewhere in these crosshairs. So first I will target reference mark and with face left, and so this is my 0 degree. Okay, let us see, this is the sun, and now I will bring the sun like this, and now I will measure time, theta angle, that is the horizontal angle from reference mark, and altitude angle above the horizon, this and this, done. Now again with the face left, I will bring the sun in the face left only in this quadrant, cross. So I brought the sun from third quadrant to the first quadrant, and now I will measure time, theta and alpha. Okay, now I will go back to the reference mark and I will change the face. Well, with the face left, I should get 0 degree answer again. Now I will change the face. I will bring the face right, change the face of theodolite, and then I should have 180 degree here, very obvious if there is no error in the theodolite. Then I will again measure the sun with face right. So let us see, I am bringing the sun, but this time I will bring into the second quadrant like this. So I will bring this crosshair arrangement in such a way that sun is touching this way here. So I have measured t, theta and alpha again, third time. Okay, finally with the face right, I will measure the sun in this fourth quadrant now. I note the time, theta and alpha values. We have measured the sun in the 4 quadrants. Okay, now my observations are completed. I can check my results by bringing back the theodolite to the reference mark like this with the face right, and I should have the 180 degree angle again. Okay, now what's the advantage of this? By measuring the sun in 4 quadrants, I need not to apply the corrections for the semi diameter because I have measured the sun 4 times. So I need to apply 4 corrections. These 4 corrections will be compensating each other from the left to right and top to bottom. So positive correction, negative correction, right correction, left correction. they will compensate each other and they will cancel out. Okay, that's the idea here. What if you measure only one limb of the sun? That means if you take only one observation in either of the quadrant, then you should make correction for semi-diameter. And then you will take only one observation, that is T1, theta 1 and alpha 1. So let us go ahead. Let us see whether you have measured one measurement of sun or you have measured 4 measurements for the sun. So let us go with any arrangement. So what are the calculations? So these are the steps here. First, you will calculate the average time. It is your country standard time. That is for India, it is Indian standard time. And now you will reduce this time to the GMT, Greenwich Meridian Time, by making a correction of 5 hours 30 minutes, right? Now you will measure the theta angle, the average value of theta. Then you will measure the average value of alpha. Now we will put the corrections to the alpha. So all these corrections are given here, CR, CP and beta. Fine. This is celestial triangle that is being formed at this location and at this moment when I measure the sun at this value of alpha dash, at this value of theta and at this time value. According to the time, I will refer my star catalog and find out what is the value of declination for given time, and remember that we have already found out a GMT. For that GMT, what is the value of declination? Well, I know the declination value delta, I know the alpha dash here from observation, and I know the latitude of the place of observer. Let us calculate zenith angle, co-latitude, co-declination and calculate this value of S, which is the summation of the 3 values divided by 2. So put this formula now, this sin A by 2 here, and find out the value of A, and that is nothing but the azimuth of the sun at a given moment t. So basically it is the azimuth of the sun with respect to true north at your place. Now you can find out what's the angle of reference mark with respect to true north, and that is the azimuth of the place. Remember few things here. The duration of all 4 observations should be within 3 minutes. That means T1 to T4 should be taken within 3 minutes. What about the time? Can you find out the correct time of your watch? With the same spherical triangle, with the same set of measurement, you can also find out the hour angle. Hour angle will be measured at your celestial meridian. Okay, here I would like to say something, that when you measure the hour angle at your location, so it is the hour angle with respect to the standard meridian of the country. So what will you do now? You should make some corrections in order to find out the correct time in Indian standard time at your place. So what will you do? You will first take the difference of your meridian and the Greenwich meridian, and you will put the corrections there, so that you will bring the hour angle to the Greenwich meridian time. From the Greenwich meridian time, if you add the time of 5 hours 30 minutes, you will get the correct time of your watch by astronomic measurement at your place, but Indian standard time. So now you can compare the 2 times, the time for taking the sun observation and the time that you calculated by the astronomic calculations, and you can compare. But remember, we have made an assumption here that I am performing all 4 observations within 3 minutes, because during these 3 minutes the variation of the declination of the sun is minimum, or it is as per the requirement of our accuracy of time calculation. So you should be very careful about that. Well, now you have found out the correct time of your watch. The precautions one should take while making the sun observation. First of all, you should use the sun objective filter if you are using theodolite or total station or electronic theodolite. So on the eyesight, you should put the objective sun filter that will save your eyes from the intense light of the sun. Secondly, if the altitude of the sun is much higher, then you will need the diagonal eyepiece, because let us say altitude is more than 20 degree, it is very difficult to measure. So better to use diagonal eyepiece or perform your experiment in the morning time, because in the morning time sun is at lower altitude, below 20 degrees. Further, there is a warning that if you are using an electronic instrument like total station or electronic theodolite, first take a recommendation from manufacturer. Suppose you are using Leica, Trimble, Topcon, Pentax or Nikon, any instrument, but you should first consult this thing with manufacturer of the total station, and on their recommendation only you should use for the sun observation. because sometimes electronic circuitry is not recommended to make measurement for the sun. So be careful on this part also. Okay, now the last question. How to find out the north direction if you don't have any idea at a given place? You don't have any astronomical observation, you don't have any star catalog with you, you don't have any idea about astronomy, but simple idea I am telling you. Perhaps it is given in 7th or 8th standard book. So I am repeating that. So thanks to those knowledge and thanks to those books. Here you will find out there is some set of stars which are called Saptarishi Mandal, and there are 7 stars. So in Hindi or in the Indian system, these stars are given the name of some saints like Vasishtha or some other names, I don't remember exactly. But now if you see that if I connect these stars by line, it will create a spoon shape. So now you can see that star 4, 5, 6 and 7 are creating some kind of bowl shape, right? And star 1, 2, 3, 4 are creating the handle of spoon. Now if you connect the star 6, 7 and extend the line, this line will go to a star, and this is the pole star, Polaris or North Star. This 7-star constellation is called Ursa Major in astronomic terms, and Western name is Big Dipper. Okay. What about the pole star? How can you further confirm pole star location? The pole star itself is a member of a constellation, and that is called Ursa Minor, which is just inverted form of the Ursa Major, like this. So it is another kind of spoon, and where it is having a bowl and it is having a handle. So the pole star itself is one of the member of this Ursa Minor. So now you can confirm this kind of star constellation in the sky, and you can confirm where is the pole star. And remember, the pole star is exactly above the north pole of the earth. Okay. Further, we have given you some more information about that. Now we have find out the pole star. Okay. So there is a zenith for you, there is a pole star in the sky, then you connect this line, that is your meridian, and if you make this meridian from the zenith to north star or the pole star, and then on the horizon, this will connect you to the north direction at your celestial horizon. Well, that is the idea how to find out the north, and opposite to this north direction there will be south. Okay. What about east and west? Fine, you can find out. So if you are facing the east, on your left hand side there should be north. Now you can find out the east. So without measuring the sun, you have find out the location of east, west, north and south. So that is a simple knowledge one should have, and while at least you can now go to any open place in the night time, and you can do your study about the North Star, and you can find out the correct direction or at least approximate direction of the astronomic north at your place. I think we have responded almost all the queries so far. Well, with this idea, we are trying to conclude our module 3 here on astronomy. But before concluding, I would like to give you some information about the celestial reference system. So the celestial reference system is there, and we are measuring the extragalactic sources which are far away stars, and they are called quasars. So measuring those quasars, we are finding out the celestial reference frame for the earth, and this frame is called International Celestial Reference Frame. So similarly, we are using here the VLBI, very large base interferometry technique, in order to receive the signal from extragalactic radio sources, which are the radio signals coming from the faraway stars. Secondly, we also have terrestrial reference system that we have discussed in module 2, okay, and this is the realization of TRS is International Terrestrial Reference Frame, ITRF, okay, and ITRF is established by various satellite programs and VLBI. So GPS is one of the satellite program, then we have DORIS, we have lunar laser ranging, then we have satellite laser ranging. So using these 5 techniques, we are finding out the surface of the earth and overall adjusted value of the earth, and then we are deciding what is the rotation axis of the earth and so on. So with this, we find out the center of the earth with very high precision, and now using those things we establish our ITRF. Okay, and the relation between ICRF and ITRF is established by the rotation and using the earth rotation parameters. Okay, all this information is available with the International Earth Rotation Services, who is responsible for measuring or taking all this information from various sources, various stations of GPS, VLBI and so on. Okay, so with this we are going to conclude our module 3 here. We will see you in the next module on adjustment computation, error and accuracy. Till then, wait and watch and try to solve some problems on astronomy. It's very interesting subject. Perhaps it has been avoided because of the complexities. So try to enjoy the astronomy. Okay. So till then, wait and watch. Thank you very much.